Okay, lab 5, Slinky. So the purpose of this lab is to predict the motion of a falling Slinky and to analyze how the surroundings affect its motion. In this lab, I will use Tracker to analyze the motion of the falling Slinky in the video and a computational model to predict its motion. So the physics principles I used are stated here. I used Newton's second law, law of gravitation, which is equal and opposite to the tension force from the Slinky, and I use drag force. So to preview my results, while the bottom of the Slinky does fluctuate slightly as the Slinky compresses, it pretty much remains in the same spot. And the Slinky is the system and the surroundings are everything else. So here's my tracker video. Like I said, as the video plays, the bottom of the Slinky remains constant. And here is all of my coordinates. You can see at each time interval I have the x coordinate and the y coordinate, and the y coordinate pretty much remains the same. Here's part 1 of my computational model. I set the mass of the Slinky, and then I set the initial position vector and initial velocity vector. And then I have the gravitational constant, I have the unit vector, and I have the drag constant, which I got through trial and error. Here is part 2 for the first part of the Slinky as it compresses. So here I set the force of gravity, tension force, which is equal to the force of gravity, and opposite, and the net force. Then I did velocity and position update to update the Slinky. And then this is for the second part of the model, when the Slinky compresses and starts falling altogether. So once again, I set the force of gravity, and then I have to set the drag force because that's acting opposite to the force of gravity. So that's how I got the net force here. Then I once again do velocity and position update. So here are my results. This is the tracker model. It shows how the bottom of the Slinky remains in the same place and then starts to fall off, which is very similar to what I see here in my computational model. So here is when it's remaining constant, and here's when it starts to fall off at a very similar rate, but not exactly the same. So some possible sources of error in my lab. One potential source of error may be that there are some external forces acting on the Slinky that made the results slightly different than the computational model. Another potential source of error is that I slightly misplace the point mass in the tracker video. And lastly, discussion. So basically what causes the bottom of the Slinky to remain in the same spot as the rest of it falls is that the forces acting on the bottom are obviously the force of gravity, which is acting downward, and the tension force from the rest of the Slinky, which is acting upward. So when you initially let go of the top of the Slinky, it takes a while for the bottom of the Slinky basically to realize that the tension force has gone to zero. It has to travel down the Slinky. And when it finally travels down and the Slinky compresses, that's when it knows, okay, there's no longer a tension force, and then it starts falling. So that's basically kind of what causes this interesting, I guess, case with the Slinky.